All right, so for today's video lesson, we're going to introduce our last unit, atomic physics. And the first chapter we're going to explore is atomic structure. Okay, so just an overview of what we're going to cover in this unit. So in chapter 15, this is like development of atomic theory. Okay, this is kind of ties into what you would have learned in Science 10 about the development of the atom in the chemistry unit. This is just going to be a little bit more detailed than that, okay? So chapter 15, we're going to learn about the discovery of the electron from Thomson. He devised a model called like the raisin bun or the plum pudding. This is where we had electrons were kind of embedded throughout the atom, and where there was not an electron, it was a positively charged area, just kind of the space that was in between the electrons was positively charged. Okay, next we will move on to Rutherford. He had like the planetary model, where he had electrons orbiting a positively charged nucleus. Okay, and then later on that year, Bohr comes along and he actually works alongside Rutherford, and then they develop the Bohr model. Okay, quite the elegant name for it. And then lastly, and what we have currently, our idea of the atom is the quantum cloud model. And this is just essentially the probability of finding an electron in one particular location, okay? Quantum or the quantum cloud model was from the works of Einstein, Niels Bohr as well, and Max Planck. Okay, and there were other scientists that worked on that development as well, but those were kind of like the main three. Okay, so we're going to look in depth at some of the experiments that these scientists conducted to allow us to acquire a more accurate model of the atom. Okay, so that's what chapter 15 is going to look like. Chapter 16, we have nuclear physics. Or nuclear reactions. Okay, so we are going to talk about the idea of the isotope, right? This is something that has the same number of protons, but a different number of neutrons. Again, that ties into your Science 10. We're going to talk about the binding energy. So this is the energy required to break apart the protons and the nucleons within a nucleus. We are going to talk about radioactive decay. So 3 of the main types will be alpha decay, beta decay, and gamma decay. Okay, those are all types of radioactive decay. Okay, well, we're going to talk about half-life within the radioactive decay. We'll talk about fission and fusion a little bit more. Okay, so that is chapter 16. And the last chapter that we will cover in Physics 30, this is subatomic particles. So remember we talked about quarks and leptons a couple weeks ago. So we will talk about that a little bit more, and we will also briefly talk about the grand unified theory of physics. And this is essentially simulating or a theory that represents the state of the universe at a time very shortly after the Big Bang. All right. So discovery of the electron is our first topic. And this was done by J.J. Thomson in 1987. Okay, so he used a cathode ray tube, and basically he observed that the movement of cathode rays in the presence of a magnetic field would cause those cathode rays to deflect. Okay, when a charged particle is deflected due to the presence of a magnetic field, we call this the deflecting force. Okay, and yeah, this setup here allowed Thomson to discover the electron. Okay, so I have a really good video here. It summarizes the development of the atomic theory and also talks about the experiments that were conducted. They do a really good job of kind of visualizing the entire process. Okay, so I have included a document that has all the links to these videos. So make sure you take the time to watch that. I would encourage you to pause this video and go ahead and watch the development of the atomic theory first. All right, so we will start with the Greeks. Okay, so this is in, around 500 before Common Era. So about 2,500 years ago. Right, so quite some time. And we start with a gentleman named Democritus. Okay, he was a philosopher that proposed that matter was made of indivisible particles called atoms, which was derived from the word atomos, meaning indivisible. Okay, so he did not think that the particles in the observable world around him could be separated into anything less than those particles. Okay, so atoms being indivisible. Okay, next we have John Dalton comes along. So he has the billiard ball or the solid sphere model. And this model was based on experimentation and not on reason, unlike Democritus. Okay, Greek philosophers were typically scientists, and they conducted thought experiments more than actual quantifiable experiments. Okay, and through his various experiments, Dalton came to the conclusion that all matter is made up of atoms. Atoms of an element are identical, so oxygen atoms would be, oxygen atoms in Canada would be the same oxygen atoms, or the same properties anyways, as one that would be in China, for example. Each element will have different atoms. So those of sodium will be different than those of helium. Okay, and atoms of different elements will combine in constant ratios to form compounds. So this is like carbon dioxide or nitrogen dioxide. And atoms are rearranged in reactions, in chemical reactions. Okay, so Dalton came up with some pretty important ideas. A lot of these kind of hold up still today, although we do have a little bit of a better understanding of some of these conclusions that he reached. Okay, his ideas account for the law of conservation of mass. So this states that atoms are neither created nor destroyed in chemical reactions. They're just transformed from one state to another. Okay, and he also, his ideas are responsible for the law of constant composition. So this is elements combining in fixed ratios. So this would be like nitrogen dioxide, diatomic oxygen, carbon dioxide, water, etc. All right, so that was Dalton, and he had like the solid sphere model. His essentially just was a circle, kind of like a billiard ball. Okay, just to touch base with our buddy Michael Faraday. So in the mid 1800s, so before the quantum revolution, essentially, he used electrolysis. So he applied electricity to a solution, and he was able to decompose that solution into the component elements. So if you were to apply electricity to, say, water, okay, the gas would, or the water would break up into its components, so hydrogen gas and oxygen gas. And because there are 2 moles of hydrogen, we should expect there to be more hydrogen gas being permitted or produced during the hydrolysis of water. Okay, so Michael Faraday, few inventions along his day. And from these experiments, he concluded that electricity has an important role in holding compounds together. And we will talk a little bit more about electricity and energy within the mass of a nucleus in our nuclear reactions in chapter 16. Okay, so the next model of the atomic structure is J.J. Thomson. This was quite important. He was the gentleman who discovered the electron, right? And that was in 1897. And yeah, so his model was the raisin bun or the plum pudding model. And although it's still useful in today in describing chemical properties and phenomena, it does not explain the role of electricity in the structure of the atom. The idea is if we have a positively charged core and negatively charged electrons surrounding that positive core, the idea was that essentially the negatively charged electrons would be attracted and it would perpetually fall into the positively charged regions if it's larger, okay? So it didn't really stand up to today's understanding of the theory, but at that time, you know, around the 1900s, he was pretty good for that time, and he did discover the electron, so let's give him some credit. Okay, so when he discovered the electron, he used this apparatus, which was developed, you know, about 50 or 40 years before he discovered the electron. This is called a cathode ray tube. So when they were to connect a battery to a cathode ray tube, and when they mean partly evacuated, they're trying to remove all of the air from the tube to allow the electrons to move with as little resistance as possible. Okay, so when a voltage was applied, electrons or a cathode ray would move from the cathode to the anode. I know this is a little backwards from your chemistry, okay? Yeah, so we just got to get past that. In chemistry for electrolysis, the cathode is positive and the anode is negative. In this case, for the cathode ray tube, the cathode is the negative electrode, okay? So it's a little bit backwards there, but we just got to take that into consideration. And yeah, so this was named the cathode ray tube because the glow of that emitted electron beam was most intense around the cathode, where the electricity was discharged into the tube. Okay, this is another really good video to explain what a cathode ray tube does, how it works, and how the presence of a magnetic field will influence or deflect the path of the traveling electrons from the cathode. Okay, so pause this video now and please go ahead and watch video number 2 on the topic 15.1 video list, please. Okay, so now that you have a little bit of a better background of a cathode ray tube. So typically the one that Thomson used, it was long and cylindrical. Okay. Gentleman named Crookes comes along and he bent the cathode ray tube. So he kind of turned it into a sphere. And he found that some of the cathode rays would either absorb or reflect or refract. And some of these properties are similar to those of electromagnetic radiation. Okay, so we're starting to make that connection between cathode rays or electrons, traveling electrons, and EMR. So we know now that EMR and cathode rays are the same thing, right? But yeah, so these will travel in straight lines at high speeds, and they will react with things that will get in the way, right? So in this image here, we have cathode rays being beamed throughout a cathode ray tube. It interacts with the anode. It's attracted to the metal cross. So those negative cathode rays are going to be attracted by the anode, the positively charged metal cross. And because those electrons will be absorbed by the metal cross, there will be an absence of light or a shadow at the end of the cathode ray tube. Okay, this is a pretty important idea. Cathode rays were one of the first technologies that were used in televisions. So that is pretty interesting. Okay, now we have a little bit better technology. We have LEDs and LCDs. Okay, but at the time, cathode rays were pretty important invention. For one, to discover the presence of the electron, and also for entertainment purposes. Okay, however, unlike EMR, we can deflect cathode rays, right? Because we know that cathode rays are negatively charged. So if we apply, or if we bring a magnetic field close to that, the interaction between the electric charge and the magnetic field will cause those cathode rays to be deflected. Okay, so from from the data produced from these experiments, Crookes concluded that cathode rays must be composed of charged particles. So from that work, or kind of at the same time, in 1897, J.J. Thomson comes along and he shows that cathode rays were particles, which was predicted by Crookes, and that these particles were actually negatively charged. Okay, in those videos, when he brought the magnet close, the positively charged side of the magnet, which is the north end, would attract and deflect those traveling electrons. Okay, so from these experiments, he was able to calculate the charge to mass ratio, so the Q/M ratio, to be of these particles, of these unknown particles, being 1.76 times 10 to the 11 coulombs per kilogram. And today, we know these negatively charged particles to be termed as electrons. All right. So Thomson had his straight cathode ray tube, which you guys have seen some videos from. And he also manipulated that cathode ray, or that cathode ray tube, so it'd be in a circular, similar to what Crookes had done. And when he did this, and when he would shine a cathode ray through a cathode ray tube, and he applied a magnetic force around that cathode ray tube, he noticed that the rays would move in a arc manner, right? It would turn into a circular motion instead of moving straight. So based on that, and knowing what we know about deflecting charged particles from Unit B, he concluded that the reason or the cause for those cathode rays to move in a circle, so the centripetal force, was a result of the motor force. So a result of the magnetic field that was present. So he did a little bit of formulas and calculations to allow him to discover some things, and we will get to that in a bit, okay? So from his experiment 1, so he created a magnetic field around a cathode ray tube, and the magnetic field deflected the cathode rays in a circular arc. So therefore, the motor force is responsible for the centripetal force. Okay, so the motor force is QVB, and the centripetal force is mv squared over r. And here I'm just showing you the derivation of how he found the charge to mass ratio for cathode rays. Okay, so we're looking to solve for Q over M. So let's do a little bit of rearranging. So we have V on both sides. So we can get rid of that. We are solving for Q over M. So let's divide both sides by B and both sides by M. So we are left with Q over M is equal to V over BR, and that M canceled. Okay, remember, just a reminder that this formula that I used here, Fm is equal to QVB. This is the deflecting force. Okay, so he was able to calculate the charge to mass ratio for a cathode ray. But at this point here, we still need to find V, okay? Measuring the speed of cathode rays was quite difficult to do, right? Because they travel so quickly. So he used another experiment to kind of get around the fact that he couldn't measure for V, and he did this indirectly. Okay, so this is just in summary what we just derived here. So from the motor force causing the centripetal force, he was able to arrange these formulas for the charge to mass ratio to equal the speed of the particle divided by the magnetic field intensity multiplied by the radius. Okay, so this is his second experiment. So as I mentioned, speed was so difficult to measure directly. So he developed a method of calculation based on another series of experiments. So he used a magnetic field and a balancing electric field. Okay, so what we mean by a balancing electric field, it was just adjustable. So he could adjust the strength of the electric field. And he was trying to find the ratio so that between the electric field strength of these plates here. Okay, so the electric field strength and the magnetic field, which we see going across in our magnets. Okay, he wanted to make sure that those electrons that were passing through would be undeflected. Okay, so for those electrons to, or the cathode rays to be undeflected, the Fe, or the electrostatic force, moving on an electron, or the electrostatic force acting on an electron moving through an electric field must equal the deflecting force. Okay, so Fe is equal to the deflecting force. So Fe, the force moving a charge through a electric field, is equal to Q times E. And the deflecting force is equal to QVB. Okay, we have Q on both sides, so we can get rid of that. And we want to write this formula in terms of velocity. So we will divide by B on both sides. Now we are left with V is equal to E divided by B. So he found this apparatus here allowed him to find the ratio between the electric field strength and the magnetic field strength that would allow that cathode ray to pass through the magnetic field and the electric field undetected. Okay. So, and this is what we just derived. This formula here is not on your formula sheet. So be able to derive this formula from Fe is equal to Q times E, and from Fm is equal to QVB, okay? This is not on your formula sheet, so when you write the final, you will not get this. However, I would encourage you guys to write this on your own personal formula sheets, okay? Okay, so based on those two experiments, if we combine the above equation, so V is equal to E divided by B, and if we combine that with the equation derived from experiment 1, so Q divided by M is equal to V over RB. Sorry about that. Q over M is equal to V times RB. Now we know that V is equal to E over B, the electric field strength divided by the magnetic field. So we can substitute that in. So we will get Q over M is equal to V, which is E divided by B. And that is going to be divided by 1 over RB. Okay, so we can simplify this. So we find the charge to mass ratio is equal to the electric field strength divided by B squared, the magnetic field strength squared, multiplied by the radius. Okay, so this formula right here and the derivation of that formula allowed Thomson to find the charge to mass ratio for an electron. So that was quite an important discovery. Okay, today, because we know the mass and charge of an electron, we can determine electron speed if we know the magnitude of the potential difference for which the electron passes, okay? So remember, potential difference is delta V. So if we know delta V, we can find the velocity of the electron. Okay, and we're going to do one more derivation there. So voltage is equal to change in energy over Q, over the charge. And we know if the change in energy is kinetic. Is 1/2 mass times velocity squared. So we will substitute this into that formula here. So we get V is equal to 1/2 mv squared divided by Q. So let's go ahead and solve for V here. Multiply both sides by 2 and by Q. Divide by M. And lastly, take the square root of our velocity. Okay, and then we will get velocity is equal to the square root of 2 times Q times V, which is our potential difference, divided by the mass of the electron. Okay, again, this is not on your formula sheet for the final. So make sure you are able to reach this formula from these two formulas up here. Okay, again, you should write this on your own formula sheet, but just know that you will not get this formula given to you when we write the final. Okay, so this slide is just summarizing what we have just talked about and what we just derived. All right, so let's get into some examples here. All right, so here we have a beam of electrons, which is passing undeflected through a 2.5 Tesla magnetic field. So we know the magnetic field is 2.5 Teslas. It is moving at right angles, so it's perpendicular, so we don't really need to worry about our QVB sine of theta formula. Okay, it's just QVB. And we know the electric field strength is 60 newtons per coulomb. Okay, and don't get too caught up about the units there. Just be familiar with electric field strength being given in newtons per coulomb. Okay, so a beam of electrons is passing undeflected. So if it is undeflected, then the electric force is equal to the motor force. Okay, so the electric force moving a charge through an electric field is Q times E, and the motor force is QVB. Okay, we have Q on both sides, and we are asked what is the velocity of the electrons traveling. So let's solve for V. So divide both sides by B. And then we get V is equal to electric field strength divided by the magnetic field. So we have 60 newtons per coulomb divided by 2.5 Teslas. And this will give us a velocity equal to 24 meters per second. And 2 sig digs there for because of our electric field strength. Okay, and if you're asking yourself how on earth does a Newton divided by Coulomb divided by Tesla work out to be meters per second, let me show you. So a Newton is a kilogram meter squared per second, and a Coulomb is seconds per ampere. So I'm just going to write newtons per coulomb. That's my Newton divided by second amperes. So that's my Newton per Coulomb, and then divided by Tesla. And a Tesla is kilograms in the numerator and seconds squared amperes in the denominator. So I'm just going to write it like that. And we will cancel what we can. So kilograms will go. Sorry, my meters is wrong. It should just be to the 1 because it is a Newton. Newton is kilogram meter second squared. Okay. But yeah, so we have amperes will cancel. And we have 1 divided by seconds squared. I'm just going to rewrite this to make it a little bit more simple for us to understand. So we have meters per second, and then we have 1 over seconds left. And one over seconds. Oh, I should have had a squared there. That's why I'm off. Okay, so there's my squared meters per second, and then 1 divided by seconds squared is seconds squared over 1. So seconds squared will cancel, and then we're left with meters per second. Okay, so anyways, that's how the units work, and you don't need to do your unit proof every time. Okay, you should by now be familiar with velocity being in units of meters per second, but if you were curious about how the units work, that is how we did it there. All right. Okay, so question 2, what magnitude of electric field? So we're asked, what is the electric field? We'll keep protons from being deflected. So we have a proton. What will keep them from being deflected as they move at a speed? So velocity of the proton is 10 meters per second through a magnetic field of 0.05 Teslas. Okay, so we have a proton here. And we just derived the formula we want to use for this one. So you don't have to do it every time, right? But just, for the first time that you are seeing that, you should be able to reach that formula from Fe is equal to Fm. Okay, so V velocity is equal to electric field strength divided by the magnetic field strength. We are solving for the E. So let's write our formula in terms of E, multiply both sides by B. Electric field strength is equal to the velocity times the magnetic field strength. So 10 meters per second multiplied by 0.05 Teslas gives us an electric field strength of 0.5 newtons per Coulomb. Okay, and again for units, we have meters per second multiplied by kilogram per second squared ampere, which is a Tesla. So this will give us meter times kilogram over second cube ampere, which from last question tells us it's a Newton per Coulomb. Okay, again, just get familiar with electric field strength for these types of problems being in Newtons per Coulomb. All right, moving on. So As we're starting to just do some repetition in these problems, I would encourage you to pause the video and try them on your own, and then watch the video to compare your answers at the end. All right, for our next one. So what magnitude of magnetic field will stop ions from being deflected when they move at a speed of 75 meters per second through a 150 Newton per Coulomb electron field? Okay, so we are looking for the magnetic field. So what magnitude will stop them from being deflected? So we want to use the second experiment from Thompson. Okay, that is our V is equal to E over B formula. Okay, we know the speed is 75 meters per second and the electric field is 150 newtons per coulomb. So let's write our formula in terms of B. By V. And we're left with magnetic field strength is equal to electric field strength divided by the velocity. Okay, electric field strength is 150 newtons per coulomb divided by 7.5 meters per second, which will give us a magnetic field strength of 2.0 Teslas. All right, motoring along. No pun intended. All right. Okay, so this question here, find the charge to mass ratio. So we're looking for Q over M. Charge to mass ratio for an ion that travels in an arc of radius 1 centimeter. I'm going to go ahead and convert that to meters right now, which is 0.01 meters. We know the speed is 1,000 kilometers per second. So again, let's go ahead and change that to meters per second. So this is 10 to the 3 kilometers per second. So this is 10 to the 6 meters per second. And we also know the magnetic field strength is 1 Tesla. So we know this ion is moving in a circular motion. So our centripetal force is caused by the magnetic field present. So the centripetal force, mv squared over r, is equal to the deflecting force, which is qvb. And we are solving for the charge to mass ratio. So we need to do a little bit of manipulating here. So let's clean up our velocities first. And we want q divided by m. So divide this side by m. So cancel, divide by b. Okay, now we have our q over m on one side of the equation. So we can rewrite this. So charge to mass ratio is equal to the velocity times the radius multiplied by the magnetic field strength. Okay, so let's go ahead and punch in our values. So velocity is 10 to the 6 meters per second divided by our radius, which is 0.01 meters, multiplied by the magnetic field strength, which is just 1 Tesla. Okay, punch these into your calculator. We get a charge to mass ratio equal to 1.0 times 10 to the 8 coulombs per kilogram. Charge is in coulombs. Mass is, of course, in kilograms.